Good morning, ladies and gentlemen. First, I would like to apologize for not being with you in presence. I would certainly have liked to be there and to have a beer with you, to discuss with you in person, but as you all know, Corona situation doesn't permit certain things, and travel is one of the restricted parts. I'll try to do my best with this recorded presentation, which I think is a bit more easy to follow than a Zoom where you only have the slides on the screen. I would like to talk about mechanochemical, mechanocatalytic reactions in ball mills and cover a number of different things, but before I start, I would like to give you, it's for me the first example where a mechanical breaking of a individual chemical bond has experimentally been shown. It's a paper about 20 years old, 1999, and what these people have done is they have put a polymer chain, a polysaccharide, on a surface where it forms bonds to the surface. Then they brought the tip of an atomic force microscope to the surface and then slowly pulled away the tip and recorded the force. And what they found in the force curves are tiny little steps here. When they extended, pulled away the tip from the surface. They did numerous experiments, did very proper statistics, and at the end could really demonstrate that each of these steps is the breaking of one bond of a sugar unit to the surface while pulling away this molecule from the surface. And this was on the atomic level, I would say, one of the very first examples where a mechanical force to break a bond was used. Mechanochemistry, on the other hand, as a macroscopic tool, is much older. The first report dates back to ancient times. There is a text from Theophrastus called On Stones, where he describes that if you grind cinnabar in a copper mortar, then you form elemental mercury, and the reaction is pretty clear. The cinnabar is mercury sulfide, the sulfur reacts with the copper, and the metallic mercury is liberated and visible as a mercury drop. That's the first recorded, at least as far as I know, recorded example of a mechanochemical reaction. Then mechanochemistry, milling materials has been used over the years up to today, but I have to say when I entered this field about 20 years ago, this had always a bit of voodoo-like character to me, because the results were often very difficult to reproduce. It was unclear what was really going on. And so I was really skeptical when I initially started to work on mechanochemistry. By now I would say I know it is a true effect. You can really do amazing things with milling and with respect to a chemical reaction. But one has to be careful to record the conditions very meticulously and precisely, because mechanochemistry, there are many more parameters than just for a regular chemical reaction. Now, by now, mechanochemistry has been used for quite a number of different things. We are talking about the synthesis of new compounds. Atomic scale structure has been modified by mechanochemistry, and there are solid state reactions which occur during ball millings, including chemical catalytic reactions, which you can do by ball milling, and there is a number of references here, but you can find them in the literature relatively easily anyway. The types of mills are highly diverse, and this is one of the reasons why it's often not easy to reproduce mechanochemical reactions, because these mills are actually quite different in the nature of the force they exert. This is the one which is probably best known, the regular tumbler mill, where you have a drum filled with balls and the milling material, material to be milled, the substrate, and this just rotates and the balls basically roll. So this is more really a shear frictional force. The attritor is a high energy mill, a drum typically vertically placed, filled with balls, and a stera here which rotates at relatively high speed, so this is quite a high energy input in such an attritor mill, and that's scalable, that's used on industrial scale. This is one which you may know from your own laboratories, the regular shaker mill, where you have vessels on an arm and that moves with a certain frequency of a couple of 10 hertz typically. The planetary ball mill is maybe the most interesting mill with a very high energy input and a number of different forces. It's a bit like one of the joyrides on the fairground. You have a base plate which is rotating, and on the base plate you have vessels mounted which are rotating counterclockwise to the base plate. And if you have ever been on such a joyride, you know that you are really tossed about when you're sitting in this little thing which is rotating on the big place which is rotating in the other direction. So you're really shaken quite a bit. And the movement is, there is first a grinding, a frictional force while the balls roll, and at some point they fly over, hit the other wall, and there is an impact force. And so that's a nice superposition of different kinds of forces. So a planetary mill is quite an interesting mill type. And finally, we have a simuloyer, which is mimicking a bit the planetary mill with respect to force and the kinds of forces related to the attritor, but it's a horizontal mill type. So that's generally what mills we have available. Here are the mills we use in the laboratory. This is a planetary mill. Here is the support disc. Here are the rotating vessels. For the planetary mill, you can mount transducers and transmitters on these vessels and record temperature, pressure in the vessel, and so on, even while it's milling. This is the simuloyers, the bigger mills, which have a similar energy input as this planetary mill. Small size, liter scale. This little number here gives you the liter of the milling vessel, or even bigger, 20-liter scale. That's the biggest scale we have used so far in our milling experiments. Now, for flow-through reactions, this type of mill is not useful, because if you think how would you flow in gas and take out the product from these mills while they're sitting on this rotating thing and rotating themselves, this is virtually impossible. And so for flow-through experiments, we use these shaker mill types with modified milling vessels with a gas inflow, a gas outlet. Here is a sort of a funnel which brings back the powder which is carried out of the mill, and then you have the balls in here which exert the forces. These mills we can run from temperatures at about liquid nitrogen temperature to several hundred centigrades. We can run them at pressures, depending on the exact mill type, up to 100, even higher, 100 bars, partly even higher pressures. The milling material can be changed from stainless steel to zirconia, to alumina, to tungsten carbide. So there is quite a lot of variability, but any change you do changes the conditions for which certain processes occur. So this is something which you always have to keep in mind. I would like to cover 4 different examples. I will talk about the mechanocatalytic depolymerization of cellulose. I will talk about the mechanical synthesis of supported catalysts, I think very interesting in catalysis. Talk about the synthesis of materials which can be used as catalysts or catalyst supports with rather unusual properties which are otherwise not accessible. And finally, I will talk about catalysis under ball milling conditions themselves. So let's first go to the mechanocatalytic depolymerization of cellulose. Cellulose is maybe the most important single component in biomass. Wood, straw, all the structural material of plants is composed of something like roughly 50% cellulose. Then we have its other sugars, more with higher variability. And finally, the lignin fraction, that's forming wood, straw, all the structural material. And the cellulose, if you look at it, this is a polymer of glucose. So a sugar which is really useful, which by a fermentation you can convert to ethanol, by other processes to a number of different chemical compounds. So getting the glucose from the cellulose, which is called wood saccharification, a process which people have been looking for about 100 years, would be extremely interesting. Generally, if you use your chemistry knowledge, it's a simple reaction. Here we have the glycosidic bond. The glycosidic bond can easily be cleaved by acid catalysis, and you would get the monomeric glucose. The problem is, under the same conditions where we break the glycosidic bond, the sugars really like to react further. This is a polyol. One of the processes occurring is a dehydration which forms an aldehyde. Then you have alcohol, aldehyde, you know all that. Then aldol reactions take place, and that leads to very ill-defined product mixtures which are called humins. Basically, you get a brown stuff formed under the reaction conditions, and you can basically not use it for anything. So the clean conversion of cellulose to glucose would be a very interesting reactions. And as I said, studied for about 100 years. We have found in a number of experiments that if you impregnate the cellulose with a proton, basically sulfuric acid or another acid with about the same strength, and mill, then you cleave the cellulose change very efficiently with almost basically no side products to the glucose or glucose oligomers. This is shown here. If you impregnate cellulose with, let's take this entry here, sulfuric acid, mill for 2 hours and add water, you dissolve the whole cellulose. And this is literally really the experiment. You take a paper tissue from your pocket, which is essentially pure cellulose, impregnate it with sulfuric acid in ether, you mill for 2 hours, add water, it's a clear solution. And you have glucose oligomers in there, and it also works for lignocellulose. Here you see a similar experiment with sugarcane bagasse. This is what's left over when you take the sugar out of sugarcane. Beechwood, pinewood, strawgrass. Depending on the conditions, you get 100% conversion, at least here for sugarcane bagasse, beechwood. If you mill longer, you also get 100% conversion for the others. This is 2 hours of milling. So totally water-soluble products, and the solutions look like this. This is when you mill pure cellulose. This is a water-clear, colorless solution. If you mill beechwood, well, you have the lignin components in there which give the brown color, but it's still a clear solution, which you cannot see on the slide, but you have to take my word for it, it's a clear solution. If we do mass spectrometry of these solutions, you find you have a maximum at a mass of about 800 to 900. This is glucose or glucose xylose sugar 5 mers. Overall, from the monomer to the roughly decamer, we have different sugar oligomers with a maximum at about 5. The same holds for the lignocellulose. For this was sawdust, beechwood sawdust we here decomposed, with a bigger, more intense background. The background is due to the lignin, which decomposes, depolymerizes to more ill-defined compounds than the pure cellulose. The interesting part here is that you can even use this process for a fractionation of the biomass into different fractions, into the pure sugar fraction, into the lignin fraction. So you would add the acid to the substrate, remove the solvent, mill, you add water, you have a clear solution, and then you heat it up, and the sugar depolymerizes, the lignin then repolymerizes. You filtrate, you get a solid lignin fraction, which looks a bit like chemically also like a very high quality organosulf lignin, doesn't contain the sulfur which you normally have in a normal lignin, and the solution contains the sugars. With this reaction I actually did something which is recommended in very old textbooks from maybe the 19th century, and it's not recommended nowadays anymore. I did it anyway. I did the taste test. So I neutralized this solution, stuck in my finger, licked and it's a sweet solution. You taste glucose in the solution, which you recover from a milled depolymerized wood sample, beechwood sawdust. So a sweet solution from beechwood sawdust. So an interesting approach, and then you can go all the way from the sugars to hydroxymethylfurfural, produce foods from it, produce chemicals from it, let it ferment to produce ethanol. So a wide variability of different possibilities which you have. Now, coming then to the mechanochemical synthesis of supported catalysts. We all know supported catalysts are the workhorse of the catalysis industry. The one in your car exhaust is a supported catalyst, and the way it's normally done, it's a pretty complex process. I took this from this publication because I thought it was a nice pictorial representation. This is not my paper, it's from the group cited here. You can dry impregnate, you can wet impregnate, you can do deposition precipitation, whatever. It's always a solution-based process. You always have rather dilute solutions. You have to filter, you have to dry. So it's kind of a complex process. And we thought, actually, we accidentally stumbled over it. I later show you where it happened. Can mechanochemistry be used to produce supported catalysts where you have a support material, you mill it together with metal powder, macroscopic metal powder? Is that suitable to get a high dispersion of metal particles on the support? And if I ask this question and have it as a topic in the talk, well, of course it's possible. Here are two examples, gold on alumina, gold on titania. So you take macroscopic gold powder, about micrometer particle size, just precipitated from tetrachloroauric solution. You mix it, just shake it together with a support in a vial, fill it in a ball mill, and then you mill for 2 hours and see what you get. And what you get is, here the bright spots in the electromicrographs are gold particles. Here's the 100 nanometer scale bar here as well. And you see both on the titanium and the alumina, and we have many more examples, we have tiny little gold particles formed from macroscopic gold powder. Particle size distribution in this case about 4 nanometer, center here 3.5. So this is the typical size range you would normally get by this kind of reaction. What happens during the milling, here for the example of titania, this is important for something which we discuss a bit later. Here is the unmilled titania, that's the anatase polymorph of titania. In addition, we have here the gold reflections. Here is the gold reflection. If we now add gold and mill for half an hour, sharp reflections of the gold particles which we have present. And then you see the final one, the gold reflections are so broad they're almost invisible. And the titania is not anatase anymore, it's rutile. Rutile is the thermodynamically preferred form. So during milling, you also induce phase transformations between different crystallographic phases. This is something to always keep in mind. The catalysts are essentially as active as the reported active gold on something catalysts. If you compare it with catalysts synthesized by an impregnation process, they are actually way more active. If you compare them to the most active catalysts reported by a very elaborate processes, they are not as active, but they are actually pretty decent catalysts for CO oxidation. So the gold is really in high activity form in these catalysts. Incidentally, I mentioned this here. Here we supported gold on gamma alumina, compared it to the literature data for gold on alpha alumina. There is a reason for it. We convert the oxide to the thermodynamically most stable form. So during the milling, we convert actually the gamma alumina to the alpha alumina. I'll show you that in a minute as a tool for synthesis, in fact. We have done that for numerous examples, many different combinations of metal and support oxide, and by now we probably have 20, 30 different combinations, and for all of them, after some tweaking, it's possible to synthesize highly dispersed metal particles on the different supports. And it is also a suitable method for producing bimetallic particles. So you add metal powder of two metals, mix it with the support, mill it, and see what you get. And here is two examples, gold palladium alloy, gold copper alloy. These have been chosen because the reflections in the X-ray pattern are sufficiently far away from each other and the support patterns so that we can clearly identify it. Again, also here we have done many more examples. What you can clearly see is here in the elemental mapping, where there is gold, there is palladium, where there is gold, there is copper. So we get alloy particles, X-ray diffraction shows it, particle sizes again in the same range, something like 4 or 5 nanometers. A very simple, very efficient method for producing supported metal particles. Moving to the third topic, unusual materials. So we can synthesize materials with unusual properties, and I've already alluded to the alpha alumina. Normally, alpha alumina is very difficult to get with high surface area, and therefore it's used as a support for catalytic reactions where you need a low surface area support, ethylene oxide synthesis, for instance. Normally, alpha alumina forms at very high temperatures. So 1200, 1400 centigrades. So you have an alumina precursor, you calcine it, it goes through some transition alumina, kappa, theta, gamma alumina, and eventually at very high temperatures we have alpha alumina. The problem is, if you go to 1400 centigrades, the alpha alumina is obtained as big particles. They are not nanoparticles, they are big, and you have a few square meters per gram specific surface area. There is a known pathway which allows the synthesis of high surface area alpha alumina. It's this pathway up here where you go via the diaspore, where the oxide sublattice is already in the same structure as the alpha alumina oxide sublattice, which means you can, under relatively gentle conditions, so here 550 centigrades, transform the diaspore to the alpha alumina. The big problem is the synthesis of the diaspore. 723 Kelvin, 1200 bar pressure, hydrothermal conditions, 35 days. That's not a really viable synthesis protocol. And so a different method would be great. And we found this different method. Ball milling for less than 3 hours at room temperature of gamma aluminium oxyhydroxide of boehmite gives you alpha alumina, which you can see here. This is the starting gamma the boehmite. After 3 hours and heating to 823 Kelvin, to convert the tiny traces of diaspore, which we still have, gets us an alpha alumina. And this alpha alumina has 120, 130 square meters per gram. Here you can see the X-ray patterns, so very fine grains of a few 10 nanometers, 20 nanometers size, corresponding to this very high surface area. Very simple process, 3 hours milling. If you mill longer, you don't even have this diaspore tiny byproduct. At this point, I want to tell you one dirty, literally dirty little secret of the people who do ball milling. You always have contamination from your grinding media, from the balls, from the vessel. And so this is done in a tungsten carbide milling jar. After milling, the powder looks gray, starting from the white boehmite powder. And the gray color comes from the tungsten carbide. Fortunately, you can remove it by an oxidative treatment with nitric acid and hydrogen peroxide for a very short period of time. Then you get white powder, 125 square meters per gram. Tungsten contamination goes down to almost zero. And if you choose other milling materials, well, then you can produce materials with unproblematic contamination. Such a high surface area alpha alumina can actually bring advantages in catalytic reactions. We use them as supports for a Fischer-Tropsch catalyst, cobalt here on gamma alumina, on regular alpha alumina, low surface area, and on this ball milled alpha alumina. The performance of the catalyst on the ball milled alpha alumina is essentially the same as on the conventional cobalt on gamma alumina. But the gamma alumina, when we hydrothermally treat it for 5 hours, just with water in the gas phase, it converts actually back to boehmite. The alpha alumina, on the other hand, here ball milled and then pre-treated at 1073 Kelvin, remains alpha alumina even for 20 hours under hydrothermal conditions. So this is a very stable support, and we believe that we can produce better catalysts based on this support material. We can also use ball milling to modify the surface, to make it hydrophobic, for instance. Normally you would do you would do a silylation with an organic group bound to the silicon. Regularly, you would use a trimethoxy alkyl silane, 120 centigrades in toluene under reflux for 3 days, and then you would functionalize the surface and get these alkyl silyl groups on the surface. If you ball mill, 5 minutes, very gentle conditions, no solvent, you just add the silylation agent, you add the powder to be modified, you get essentially a surface covered by an alkyl silyl species on the surface. Here you see that we have the CH stretch in the infrared on these material, clearly indicators for the silylation. It loses, if you start with SBA 15, ordered mesoporous silica, it loses about 18 weight%. This is the combustion of the alkyl group on the surface. Structure doesn't change, surface area and volume is reduced because you have these pending chains reducing the free pore space of the silica. And if we do the NMR, you see clearly the signature of the T groups, so silicon atoms with alkyl groups bound to them. So this is a really nice method for functionalization of the surface of materials. We also tried it for alumina and other oxides. It's a pretty general method, very gentle milling, 5 minutes, and a clean reaction. Coming to the last part, which for me is maybe even the most interesting one. What happens if you run a catalytic reaction while you are milling, while you are shaking the catalyst powder, thus creating always new surface area, creating defects which may have a different reactivity? Does this affect catalytic performance? I already showed you the type of mill. We have these shaker mills. The gas comes in here, goes out here via this little funnel, and then goes into the analytical system, infrared, GC, whatever you want to attach to it. And you do the whole thing while you are milling. And if you want to, you can heat this vessel. You can put a back pressure regulator here to get a higher pressure in the vessel. So it's a pretty versatile setup you can construct based on this material. And this was our very first example, which I have to say really excited me. This is CO oxidation, guinea pig reaction. We have here CO flowing over the catalyst. In that case, this was a chromium oxide catalyst, 1 gram of chromium oxide in the mill. We start the mill and we see suddenly we get reactivity. We get about 25% conversion at room temperature if we just switch on the mill. Switching off the mill, conversion is gone. Switching on the mill again, conversion recovers. So the milling clearly induces chemical reactivity. We did all the kinds of double checks to make sure it's really the milling which affects the chemical reactivity, and it's clearly proven that it is the milling. We then changed to more complex systems. This is preferential CO oxidation, so hydrogenating traces of carbon monoxide out of a hydrogen stream to clean up gas, for instance, for feeding it into a fuel cell where you need to get rid of the carbon monoxide. What we see here is for different temperatures, from minus 30 centigrades to 100 centigrades, the conversion of CO and the selectivity to CO2. And we see something very strange. In this low temperature range here, actually both the selectivity and the conversion of the CO increase with decreasing temperature. This means a negative apparent activation energy. which is known in catalysis. If it's different processes superimposed with different activation energies, this can happen. Our interpretation is that we are here looking at the activation energy of defect healing, which are responsible for the high reactivity, and the activation energy of the surface reaction itself. And that can lead to negative apparent activation energies. If we do that in a plug flow reactor, we get the normal behavior. At low temperatures, nothing happens, essentially no conversion. We need to go to 150 centigrades to get roughly the conversion which we got in the mill at minus 30 centigrades, and we never get the kinds of selectivities which were observed in the mill. So also in reactions with selectivity problems, milling can be a really interesting method. Coming to another reaction, methane functionalization. We are still flaring lots of methane. If we had a simple method to make something useful from methane, that would be interesting. Methanol is one such example, but chloromethane is also an interesting example for a useful compound to be made from methane. So we have to chlorinate, and the way we chlorinate it is with this cyanuric chloride. This is something which is a relatively cheap compound. It's used for water cleaning in aquariums. So if you have a fish tank at home, you actually may have used cyanuric chloride for your water treatment. So it's a pretty cheap compound. If we put the cyanuric chloride in a mill with typically Lewis acid type solids, alumina, ceria are pretty good catalyst for this reaction, mill it and flow methane over it, what we see is basically absolutely clean conversion to the monochlorinated product. Almost no bi- or trichloromethane. Selectivity is 98+% for this reaction for the monochlorinated product, which you never achieve in a regular reaction. And the productivity is on the order of 150 grams methyl chloride per kilogram of catalyst an hour. This is what you get in a big industrial scale catalytic reaction. So the productivity is really high, and this could be an interesting reaction. The process is a radical process here, so the milling creates radicals, the chlorine radicals attack the methane, and you get the chloromethane. Final example, for me, basically the pinnacle of what we have done, ammonia synthesis. Ammonia synthesis is studied for approximately a century, started in the early 1900s with the work of Haber and Bosch. There are scattered reports in the literature, the ones early in the 1960s on milling in the nitrogen-hydrogen atmosphere, I would consider not as very reliable. There is a chemical looping process going first to a nitride, iron nitride formation, then reacting the iron nitride with hydrogen, and thus producing ammonia, which is a very interesting approach given here. We found we actually can synthesize ammonia under continuous conditions at room temperature and atmospheric pressures. The catalysts are alkali metal, not oxide, alkali metal doped iron powder, and we get in a batch mill ammonia formation with a yield up to 0.5%, which is for these mild conditions quite remarkable. The first experiments in a flow-through system we just analyzed by wet indicator paper. This is the outlet of the mill. You see here, this is the wet paper. It turns blue, so it's alkaline. That's ammonia. Of course, we have done that much more carefully. This is now a continuous reaction over something like 60 hours. The spikes are shutting down the system overnight and not letting the clock run further. So during night, you have to then, in the morning, flush out the gases again. And you see we get productivities of something like 30, 40, 35 micromoles per gram of catalyst. Two runs are superimposed here over, one is about 40 hours, one is 60 hours, so it's a pretty reproducible system. And even at room temperature and atmospheric pressure, this is being done here with the cesium-containing catalyst, we can still get something like 10, 15 micromoles of ammonia per hour. Really exciting reactions. We are optimizing it. Highest outlet concentration we have had was about 0.5% at somewhat higher temperature. And this got us quite a broad coverage. This was reported in Chemistry Engineering News 2 weeks ago. And we even made it into the Frankfurter Allgemeine Zeitung, which is the German biggest German regular newspaper. I would say the New York Times equivalent in Germany. With this, I want to finish. I have shown you 4 case examples: ammonia depolymerization, synthesis of supported catalyst, creation of catalytic materials which have interesting properties as the alpha alumina with high surface area, and finally catalysis under milling culminating in the ammonia synthesis. Maybe this approach could also be interesting for you at one or the other point. It's actually, if you have a mill, it's relatively easily done if you have a good workshop. And I want to thank the workshop. They did a lot in adapting the milling systems. The authors were on the title page who did a lot. Most of them are also here in the picture of our last group retreat. But those who have directly contributed are important, but it's always the work of a whole group, putting input in form of discussions and so on. I would like to thank them. I would like to thank you for your attention.